Will increased spending on digital advertisements lead to an increase in sales? Is the new drug able to reduce blood pressure in obese patients? Will the introduction of a new manufacturing process or technique lead to an increase in defects? Questions like these force us to draw inferences about the efficacy of a specific action on a specific outcome. Welcome to the mysterious world of inferential statistics, which is otherwise also called statistical hypothesis testing.
Welcome back to Learning Puri, a channel for applied learning, where you get tips and tutorials on a variety of topics just like this one. In this video, we will focus on not only unraveling the somewhat mysterious world of statistical hypothesis testing, but also to provide you tips on the correct way of conducting it. Now, you might be thinking, but why bother with statistical hypothesis testing? Can't we just go with our gut feeling or intuition? Well, the truth is that our gut feeling or intuition can often be wrong, and statistical hypothesis testing helps us make decisions based on evidence rather than just guesswork.
In inferential statistics, we study sample data and draw generalized conclusions about the population. These conclusions are tested for their validity or significance using a process called statistical hypothesis testing. But hold up, folks. Before we can even think about hypothesis testing, we need to get familiar with descriptive or summary statistics and probability distribution. It's like learning to crawl before you can walk. So, I urge you to check out these tutorials first. Trust me, it's a prerequisite to understand this topic better. Alright, let's get down to the nitty-gritty by asking, what is a hypothesis? The term is derived from the ancient Greek word hypothetenai, which means to suppose or to assume. So when we assume something, we need to test it against something and then draw a conclusion about the comparison. Therefore, hypothesis tests or statistical hypothesis testing in simple terms is a technique that is used to either compare a sample from some large data set or population with the population, or comparing two different data sets.
Since it is a statistical inference method, post comparison we draw a conclusion and infer some outcome about the characteristics of the data being compared.
For instance, we can infer whether the average day temperature in the month of November has been below 15 degrees Celsius, or whether a particular car A has a fuel efficiency of 21 kilometers per liter. Not more, not less. We can even infer whether the average height of people in Netherlands is more than 170 centimeters. These three are good examples of inference for a sample drawn from a large dataset. We can even compare two separate data sets to draw an inference on whether males on an average are taller than females, or if therapy A is better than therapy B to cure an infection. Please pause for a moment and compare the wordings of the statements used between the two types of comparisons we discussed a little while earlier. In one case, we are comparing samples with some overall or average figure of a large data set like population, whilst in the other, we are comparing between two small groups of data. Alright, moving on, when we draw conclusions or want to prove something, mathematics follows different principles of proof. In statistical hypothesis testing, we use the principle of reductio ad absurdum. In Latin, it means reduction to absurdity or reduction to impossible. The principle follows the concept of proof by contradiction. In this process, we follow three steps. First, we make and write an assumption about the problem. Then, we make a claim that is opposite to what we want to prove. And finally, we use this claim to derive a contradiction to the original assumption. What follows is that if the contradiction to the claim in step B or step 2 is found, then the original assumption will be retained. To understand this process of statistical hypothesis testing, let us take the following illustration. Capsure is a manufacturer of threaded screw-on plastic caps or seals. They manufacture threaded caps for various uses that include bottles, pipes, stopper caps for medical purposes. The caps need to be manufactured to perfect precision to provide a very good seal. One such application requires a cap of 10 millimeters inner diameter with a tolerance of 2 micrometer or 0.002 millimeters. An ill-fitting cap will result in leakage, leading to the production batch being rejected, which in turn will result in a loss to the company. In the past, the manufacturer has had a good track record of manufacturing to the exact specification of a mean diameter of 10 millimeters with a tolerance of 2 micrometer. To ensure quality, they periodically take a sample of 50 caps during the production run and compare measurements of the inner diameter with the set specifications for tight compliance. One such sample taken during manufacturing run yielded an average or mean inner diameter of 9.999 millimeters. The question to be answered over here is, should we reject the batch or not reject it? This is one instance where we must resort to statistical hypothesis testing to answer the question. Let us use the 3 steps mentioned earlier for hypothesis testing. In the first step, we will make an assumption about the problem. We know from the data provided to us that historically the manufacturer was able to manufacture a cap with an average diameter of 10 millimeters. This is the average diameter observed over several batch runs in the past. Therefore, we now must test the claim whether the average diameter of the 50 samples manufactured is statistically the same as that we have observed in the several previous batches. So we set the first claim as mu is equal to mu naught is equal to 10 millimeters. This claim is called the null hypothesis, since this is the claim that needs to be nullified using an alternate hypothesis. Null hypothesis is denoted as H naught. The next step is to make a claim that is opposite to what we want to prove. The second claim, therefore, would be mu not equal to mu naught, not equal to 10 millimeters. Simple, isn't it? The second claim is therefore the alternate hypothesis denoted by HA. Note that here we are not interested in answering whether the inner diameter is either less or more. We are interested in only answering whether it is equal or not equal to what was observed historically. Why is that so? For the simple reason that if the cap has either a smaller or bigger diameter than the specifications, it is going to be a problem. In such an instance, we will check for values on both sides, that is, the negative and the positive sides of the symmetrical standard normal curve. This approach is called the two-tailed approach for testing the claim. Now comes the third and the most important step of testing the assumption we made in step 1. The third step is to find whether there exists any contradiction to the claim in the first step. The third step consists of 2 intermediate steps, which are A, to decide the significance level, and B, the actual calculation of either the p-value or the critical value. We will understand what these values mean in a bit of time. To decide significance level and calculate the p-value and the critical value, we need to understand the concept of sampling distribution. Recall from previous videos on probability distribution for a continuous random variable, the population data distribution follows a normal or a bell-shaped curve. Using the same concept, we will introduce a new concept called sampling distribution. We generate and use the sampling distribution since we don't know what the population distribution data looks like. To generate the sampling distribution, we take a small but fixed sample from the large data set of the average inner diameter and calculate the mean for that sample. Then we replace this sample back into the original data set and draw another sample and calculate its mean as well. If we repeat this procedure for all possible permutation and combinations of the samples drawn, we will end up with a large set of values resembling a distribution. This is the sampling distribution of the mean of the inner diameter as seen in this figure. In our case, we have already done that from past data and obtained the average diameter to be mu naught equal to 10 millimeters with a tolerance or standard deviation of 2 micrometer. Here's what a sampling distribution looks like when converted to a standard normal curve. So, what's the use of a sampling distribution? Here is where we bring in another concept called the central limit theorem. It follows from the central limit theorem that any sampling distribution of a mean will follow a normally distributed bell-shaped curve. And the mean of this sampling distribution we obtained earlier is an estimate of the population mean. So, the central limit theorem allows us to make accurate assumptions about the population mean without having to go through a time, money, and energy consuming effort of measuring the entire population. Alright, having established this, let us move on and understand what is meant by significance level. Now, since we do not want to leave anything to chance, we choose a statistical significance level to check the claim for the null hypothesis. Statistical significance level indicates the percentage probability of accidentally making the wrong conclusion. It means that we will choose the percentage probability of rejecting the null hypothesis when it is true. It follows from this that if we reject a null hypothesis when it is true, we will be committing a type 1 error. Ideally, we would want to keep this error low. Therefore, the lower this percentage, the better the test. In other words, it means that we need to have stronger evidence in the form of data to prove or disprove the null hypothesis if we set a very low level of significance value. The significance level is denoted as alpha. Typically, the value of alpha is chosen from the following three options. Alpha is equal to 0.10, which means 10% chance of committing type 1 error, or alpha equal to 0.05, which means 5% chance of committing type 1 error, or lastly, alpha is equal to 0.01, which means 1% chance of committing type 1 error. Most often, the alpha is set at 0.05, which is a midway between a relatively relaxed 10% and a more stringent 1% probability of committing a type 1 error. And alpha, also called level of significance equal to 0.05, means that we accept a chance of 5 out of 100 times to reject a true null hypothesis, or we are 95% confident of not committing a type 1 error. The limits bounded within the 95% region under the curve are termed as the confidence interval. For a two-tailed test, alpha will be split equally on both sides of the normally distributed curve, that is 0.025 on each side.
With this step, we completed the first part of the third step in hypothesis testing, that is setting the significance level. If the concept of level of significance is understood, then let us move on to understand the second part of the third step of hypothesis testing. In the second part of the third step, we need to understand two more concepts, that is p-value and the critical value. Let us begin with the p-value.
If you have watched my earlier videos on probability distribution, you will note that 5% or 0.05 is also the area covered under the normal curve. This area is also called the p-value or probability value of rejecting a true null hypothesis. For a two-tailed test, which is what we are using, this value of alpha equal to 0.05 is equally split on both sides of the standard normal curve since the curve is symmetrical around the mean. This equals 0.025 or 2.5% area on either side around the mean. Note that this is the p-value that has been set as a benchmark to reject the null hypothesis. We have not yet calculated the p-value for the sample under consideration. The calculated p-value of the sample will be compared with the benchmark p-value, that is 0.05, to either reject or not reject the null hypothesis. The p-value for sample under consideration is calculated using the test statistics as follows. The probability corresponding to this z calculated value in the z table will give us the calculated p-value for the sample under consideration. The value of alpha or the value of probability of rejection remains the same, that is 0.05. This is true irrespective of whether we use normal distribution or standard normal distribution. A standard normal distribution is just another avatar of the normal distribution, except that x values are transformed to z values. Again, I will urge you to watch the previous videos on probability distribution to understand the concept of standard normal distribution. Considering this fact, if we look up the z table for a standard normal distribution, we will notice that the value of 0.025 probability corresponds to z equal to plus minus 1.96 on the x-axis of the standard normal curve. The value of 1.96 defines what is called the critical value for the sampling distribution, and it is not to be confused with the calculated z value for the sample under consideration of the test. If we do the math by substituting the values in these equations, we get the following output. Z calculated is equal to minus 3.5355 and the p-value corresponding to Z calculated equal to 0.000407 considering a two-tailed test. Both these are the calculated Z value and observed p-value respectively for the sample under consideration. Now comes the most critical part of interpreting these two values. To do that, let us go back to the standard normal distribution curve. Let us begin with the first value that we have obtained, which is Z calculated. A negative value of Z calculated indicates that it falls on the left side of the mean of the distribution. For a two-tailed test, we also consider the same value on the right-hand side of the distribution. Further, we observe that this value, Z calculated, is less than Z critical. The Z critical value defines the outer bounds of the acceptable region or the confidence interval. Any value that falls outside this region will not be acceptable since we will not be confident of not committing a type 1 error 95% of the time. The second value, which is the p-value that corresponds to Z calculated value, is lower than the p-value that we had set as a benchmark, that is 0.05. Note that the observed p-value corresponding to the Z calculated value lies further beyond the benchmark in the shaded region. The area or region under the curve beyond the critical p-value of 0.025 on either side of the population mean defines the area of rejection. Any calculated p-values that lie in this region will be subject to rejection. In other words, it again means that probability of committing a type 1 error will be more than the acceptable 95%. Therefore, whether we use the critical value approach or the p-value approach, the outcome is that we will reject the null hypothesis. In other words, it means that the measurements of the sample selected for testing do not conform to that of the historically observed values of the population. Hence, we will reject the entire production batch of seal caps owing to quality issues. Now, if you have understood this process for a single sample, then the scenario for statistical hypothesis testing is the same when we compare two different samples with each other. There are, however, a few differences. These differences merit minor changes in our approach and the equations, as we will see ahead. Let us look at these differences one by one. The first difference that we observe when we compare two samples for being statistically significant is that instead of setting the null hypothesis as mu equal to mu naught, we set it up as mu1 equal to mu2. Mu1 and mu2 are the means of the respective samples to be compared. Therefore, it follows that the alternate hypothesis will be set up as mu1 not equal to mu2 for a two-tailed approach. Secondly, we should note that in the earlier example, we were relying heavily on the sigma, that is the standard deviation of the population, to be known to us beforehand for the calculation. Most often, we will not know the standard deviation of the population. We will only have to rely on the sample standard deviations, that is S1 and S2, to work with for the calculation. Therefore, the equations undergo a slight change as follows. When using sample standard deviations, we use the t table instead of the z table. So, instead of the z value, we will now calculate the t value like so, where SP square is equal to pooled variance for two samples, S1 and S2 square are variances of two samples, N1 and N2 are sample sizes for each sample, D0 or D0 is the hypothesized difference between means. In this case, it will be 0, and degrees of freedom will be equal to N1 plus N2 minus 2. To understand degrees of freedom, please look up one of my earlier videos on the same topic. We use the student's t distribution, which is like the standard normal distribution, with the exception that the sample size could be close to 30, either below or above. To calculate the pooled variance, we make two assumptions. A, the sample sizes, and B, the variances of the two samples are either equal or close to each other.
One aspect that does not change is the application of the concept of p-value and the critical value. When we use the t statistic in the calculation, we use the t table instead of the z table to look up the calculated t statistic. Now, these two equations are complicated to handle. To calculate and memorize them is going to be a nightmare. So, if you feel overwhelmed by these equations, then relax and stick around till the end of the video. I will share with you a simple method to handle these calculations without breaking into a sweat. This will be the bonus tip in this tutorial. On that count, a quick hit on the like button for the video is most appreciated. If you're enjoying the video, then subscribe to the channel since it will help the channel immensely. Oh, and yes, you are free to share this video amongst your friends and acquaintances. You will be blessed for being generous. Alright, if the concept of two-sample test using t-table is understood, then let us look at this example to understand the two-sample test better.
The dataset represents the day temperatures taken over a period through the day in two different locations in the same region. There are 15 readings for each location. The mean temperature, the variance, and the standard deviation for these readings are mentioned as well. Now, we want to check for any statistical difference between these two temperature readings. We will use the student's t-test that was discussed earlier. We start by setting the null hypothesis as mean of temperature in location 1 equal to that of mean of temperature in location 2. Therefore, the alternate hypothesis will be set up as mean of temperature in location 1 not equal to mean of temperature in location 2. Next, we will set the level of significance or the alpha at 0.05. The average temperature and the standard deviation for the respective locations is as follows. Substituting these values in the equations seen previously for hypothesis testing, we get degrees of freedom equal to 28 for a calculated t-statistic value of minus 1.772. For a two-tailed test, these t-statistic values are plus minus 1.772. The negative value of t-statistic will be looked up on the lower side or the lower tail of the t-table distribution, and the positive value on the upper side or the upper tail. However, often the t-table values are given only for the upper tail. In such an instance, we will simply reverse the sign of the values seen in the t-table while reading them on the lower tail. Considering the p-value approach, we observe that this value of t-statistic equal to plus minus 1.772 lies in the region between 0.1 and 0.05 in both the upper and the lower tails. Since we are conducting a two-tailed test, this value is within the acceptance region, and hence we do not reject the null hypothesis. It follows from this that there is no significant difference between the two readings. This was pretty simple, wasn't it? Congratulations, you have now become a champ in hypothesis testing. Alright, with this renewed confidence, let us look at this second data set, which is also the day temperatures taken over a period through the day in two different locations in another region. In this second example, we have 10 readings from location 3 and 20 readings from another location 4, both of which fall in the same locality. Again, like the previous case, we want to check for any statistical difference between these two temperature readings. So, like before, we will use the two-sample hypothesis test. As earlier, we set the null hypothesis as mean of temperature in location 3 equal to mean of temperature in location 4. Therefore, the alternate hypothesis is set up as mean of temperature in location 3 not equal to mean of temperature in location 4. The level of significance, or the alpha, is set as 0.05. The following are the values for means and standard deviations in the respective locations. Substituting the values in the same equations as used earlier for hypothesis testing, we get the degrees of freedom equal to 28 for a calculated t-statistic value of minus 2.074. For a two-tailed test, these t-statistic values are plus minus 2.074. Again, we will follow the same procedure as earlier for looking up the t-statistic values on both sides of the t-distribution. We observe that the calculated t-statistic falls in the range of 0.05 to 0.02 on both sides in the t-table. In this case, the value appears to be in the rejection region. Therefore, we will reject the null hypothesis and accept the alternate hypothesis that there is indeed a difference between the temperatures of these two locations.
Wow, done and dusted. That was quick work. If you feel vibrant about dispatching the case successfully, you are grossly mistaken. Let us take a walk back into the past to remind ourselves of a few points.
When we were discussing the student's t-test to simplify the complex equations, we made two important assumptions. First, the sample sizes for both samples were same or close to each other. And second, the variances of both samples were same or close to each other. In this last case, neither the sample sizes were the same nor were the variances. In fact, they were not even close to each other. So clearly, student t-test fails to address the issue of dissimilar variances and sample sizes. For such instances, we have the Welch's t-test. It was created by Professor Bernard Louis Welch. He was a British statistician and an educator. Welch's test is an adaptation of the student's t-test. However, it is useful in instances of unequal variances. Therefore, it is also called the unequal variances t-test. In Welch's t-test, the t-statistic and the corresponding degrees of freedom are calculated using the following formulae. Fast forwarding ourselves through the calculations, substituting the values in the equation for Welch's test, we get a calculated t-statistic value of minus 1.537. Again, for a two-tailed test, This t statistic values are plus minus 1.537. This with the corresponding degrees of freedom equal to 10. Looking up the t table, we observe that the calculated t statistic falls in the range of 0.2 to 0.1 on both sides in the t table. Now, this appears to be in the acceptance region. As a result, we conclude that we do not reject the null hypothesis. As per Welch's t-test, there is no significant difference between the two locations.
Wow, that is a significantly dramatic turn on the conclusion. Had we resorted to using the student's t-test, we would have drawn the wrong conclusion, leading to a wrong decision being taken. Alright, having been a little wiser on the correct t-test to be used, as promised, here we are with some tips on making your life easier on the calculations. T-test can be calculated using two methods in Microsoft Excel.
In the first method, we can use the t.test function available in Excel. Let us begin with the Excel function. First, we select the necessary data arrays from the two columns. Then we enter 2 since we are using the two-tail test. Then we choose option 3 when selecting the type of t-test to choose the Welch's t-test. The output is the calculated p-value which is compared with alpha. For the second method, to use the Welch's t-test in Excel, we use the analysis tool pack add-in available in Excel. But first we need to install the add-in tool pack. To do that, go to File, Options, Add-in. You can see that the analysis tool pack is already installed for me. To install the add-in, go to Manage Excel Add-in and click on Go or OK. Once the installation is complete, invoke the tool pack through Excel menu tab using Data Analysis. You can see that there are many other t-test options available. We need to select the t-test to sample assuming unequal variances option like so. Again, choose the necessary data array from the two columns as required. The hypothesized mean difference will be set to 0 since that is the null hypothesis. After that, we set the confidence level to 95% for an alpha of 0.05. We also need to provide the cell reference for displaying the results. This can be either on a new sheet or the same sheet. We will provide the cell reference in the same sheet for simplicity's sake. Then click on OK to run the test. If you have noticed, the p-value obtained by using the t.test function and the analysis tool pack are the same. This is the calculated p-value that is compared with alpha, that is 0.05.
And that is how you can simplify all your effort on calculations around the tedious t-test formulae. I hope you enjoyed the video. See you in the next one. Till then, stay happy and stay peaceful.